In the previous video, we looked at Wind's displacement law and understood the relationship between wavelength of electromagnetic radiation from all of these stars to the surface temperature. Why do we care about the temperature? Are we packing for a trip to the star? Of course not. We want to know the temperature because using this really cool law from Stefan-Boltzmann, we can then estimate the size of the star. So this Stefan-Boltzmann law will help us link intensity to temperature. So let's write down the law. A body when heated will emit electromagnetic radiation over a range of wavelengths. We already know this from Wind's displacement law, okay, with a total intensity that is proportional to the fourth power of its absolute temperature. So what we have now is intensity, I, is proportional to the fourth power of its absolute temperature, T to the power of 4. Wow! Yes, it's to the power of 4. Which kind of makes sense, right? The effect of temperature is very, very strong on the intensity of your electromagnetic radiation. So right now, if we want to get rid of the proportionality sign and have this in an equation, we will introduce the Stefan-Boltzmann constant, sigma. All right, so let me box up the equation. Okay, and this sigma, our good little cute little sigma here. This is our Stefan. I mean, most of the time we just mention Stefan, but not to forget Boltzmann constant. So the Stefan-Boltzmann constant will also be given to you in your formula sheet. So don't forget to flip to the front page of your question paper if you need to use this constant. So it will be 5.67 times 10 to the power -8. Intensity is watt per meter square. Okay, and then this will be K to the power Kelvin to the power of -4. All right. So, but whenever we see the word intensity, okay, so let's think a little bit about intensity. Intensity is just a way to talk about power. Intensity is power per unit area. But for stars, we come up with a very fancy term. Instead of power per unit area, we call it luminosity per unit area. Okay, same thing, you guys. It's the same thing. All right. So right now we're going to start from that and try to approximate: is there a relationship between the size of the star, which is the radius size of the star, which I can sort of link to area, right, and the temperature. So my hypothesis is a bigger star is a hotter star, right? It's all about the chunk, okay? So the more thick, the more big, larger radius, larger intensity. But let's see. That's my guess. What's yours? All right, so we're going to start with intensity. Intensity is power per unit area. But as usual, we're going to take out the power, have luminosity here. Then this will be per unit area. Okay, so right now, this intensity is actually not I, right? Remember? We have intensity, which is actually radian, or this is also equal to radiant flux density, F. Okay? So I'm going to stick to this one first. Okay, I'm not gonna bother too much about F because we've used it previously. My bad, not radiant flux density, but radiant flux intensity. It's the same thing, like you guys. Can be F, can be I. All right. But the good thing here is we know that I is equal to sigma T power 4, and luminosity is L. Area is the area of a sphere. So if you look at my beautiful star at the back of my head, and let's say the star here has a radius of R, okay, and let's say if I take a chunk, of this curved, this is a sphere, right? So I just slice off a little bit. All right, so this is my surface area, A. So for the whole surface area of a sphere, okay, we're going to assume that the stars are spherical with a radius R. So then the area will become 4 pi r squared. So the surface area, I'm going to write that down for you. Surface area of the sphere is equal to 4 pi r squared. In this case, we're going to use capital R. Okay? All right, so just imagine we're taking the whole sphere. All right, so we're going to rearrange the equation a bit because we know light fraction. So luminosity or power, star power, is equal to 4 pi sigma r squared t to the power of 4. So I put all the constants in front, and then I arrange my variables, which is the radius of the star. Why do I keep using small r? Never mind. Radius of the star and the temperature of the star to the power of 4. So this is the Stefan-Boltzmann equation. Okay, but it's not a new equation, you guys. Okay, it's just I take luminosity definition or radiant flux intensity definition, and I replace the radiant flux intensity or intensity by sigma t to the power of 4. Okay, so from here, just a few things to add on. Okay, this one is your Stefan-Boltzmann constant. So good old sigma was 5.67 times 10 to the power of -8 watt meter -2 K -4. This R here is the radius of the star, aka stellar radii. Such a cool name, stellar radii, the radius of the star. All right, and this T here would be the temperature. It's more like the absolute temperature of the star, which we can estimate using Wien's displacement law if needed. Okay, so this is why this subtopic is called stellar radii. We take Wien's displacement law to give us a reliable estimate about the temperature, and then we take Stefan-Boltzmann law, which tells us that the temperature raised to the power of 4 is directly proportional to its intensity. Okay, then we put them together, and we can use this equation together with the Stefan-Boltzmann constant to find the radius of a star. Let's try an example that showcases these two equations. So in this question 3, we have a black body, probably a star, plot twist, has a maximum intensity of wavelength 1450 nanometer, and the radiation is 200 Kelvin. Okay, let's gather the information. We have lambda max, and we have the surface temperature. Okay, so we already have this data. Now we are going to look at a star called Betelgeuse. And it has been measured to have a wavelength of 850 nanometer at peak intensity and has a luminosity. Okay, so we have lambda max this, and we have its associated luminosity to be this. Okay, so you are asked to estimate the radius. So of course, what immediately could come to mind is your Stefan-Boltzmann equation. Okay, so I'm going to write that down first. L is equal to 4 pi. Remember, we gather all the constants first. 4 pi sigma, and then r squared, the radius squared, t to the power of 4. If you forget this, don't worry. This is the only equation. Okay, this is not the only equation, but this equation is given in your formula sheet, so you just copy it. Yeah. Thanks, Cambridge. Cambridge got your back. They gave you this equation. Very nice. Okay, so we're going to check it out. So right now, I have L, which is okay. I'm looking for R. All these are constant. I'm good. The only thing that is missing is temperature. So if I have temperature, I can just plug everything into the equation to help me find my value of R. So let's find temperature first. And of course, we're going to use our one and only Wien's law. Okay, I'm going to write that down. Wien's displacement law, where your lambda is, right now I can just take lambda 1 divided by lambda 2 is equal to T2 over T1, because lambda is inversely proportional to temperature. Nice. All right, so we have 1450 divided by 850. You know, if you're wondering how on earth do we measure this wavelength, you stay tuned. Stay tuned. Maybe you can think about it. You have already learned how to measure the wavelength previously. But let's say we have a reliable way to measure the wavelength of any electromagnetic radiation that we see. What do we use? What kind of phenomena do we use? All right, but regardless, let's assume we can measure and we got the answer to be 850 or the measurement to be 850 nanometer. Give it a think, guys. Okay, anyway, the temperature T2 is what we're looking for because this is our Betelgeuse. All right, and we have the temperature of the black body that will be 2000. Okay, we can now find T2. So from here, I'm going to press my calculator. T2 is 3410 Kelvin. I'm just going to take 3SF because, you know, the numbers like 1450 is 3SF. Okay. All right, so now with T2, I can then use my Stefan-Boltzmann. Let's change my pen color. Stefan-Boltzmann. You know, whenever you are using something that is new, it is useful for your brain to repeat because it helps with memory, right? So L will be equal to 4 pi sigma r squared T to the power of 4. Let's substitute 3.1 times 10 to the power of 31. 4 pi sigma is 5.67. Please check your data sheet. Times 10 to the power negative 8 r squared. We have temperature 3410 to the power of 4. Okay, remember prefixes are important. So from here, we can calculate the value of R. So by my calculator, this is 5.67 or 5.7 times 10 to the power of 11 meter. It's a very big star, you guys. All right, so that's it for this kind of question. So sometimes you will have to use Wien's displacement law to figure out what the temperature is. So we're going to look at a star and compare with another star. Then we can find the temperature. And once we find the temperature and we can measure the luminosity, which is essentially power, then we can actually calculate the radius. Okay, so let's put all of this together in a flow chart or a summary. Let's quickly summarize everything we have learned so far for this entire astrophysics chapter. Okay, so that we can orientate ourselves, right? So remember when we started this chapter, we said we look at the night sky, but what are we looking at? We are observers, right? And unfortunately, most of us, we can only gather data on planet Earth because we're kind of like earthbound. So this is the Earth observer. But what were we looking at? Okay, so first thing we looked at was radiant flux intensity, aka wow, so bright. Okay, I'm gonna write here. So bright, the star. Okay, so radiant flux intensity. Starlight, star bright. First star you see tonight. Okay, so radiant flux intensity. So we can measure basically the amount of luminosity over 4 pi squared. But this radiant flux intensity is not alone. We could also look at standard candles, right? So in this chapter, we actually recorded a little bit more because we sort of like need to understand what standard candles are. Okay, so we provided a few examples. Okay, may or may not be part of your syllabus, but it doesn't matter. It doesn't hurt to learn a bit more, isn't it? The world is a fascinating place. Okay, so we look at the Cepheid variable, the stars where the intensity decrease, increase, decrease, increase with time. Okay, and then we also looked at the type 1 supernova, where there is a sudden explosion, there's a peak intensity, and then it drops. Okay, either way, based on what standard candles are, name also standard candle already, right? So it is something of known luminosity. So from here, we actually can figure out what the luminosity is. And figuring out luminosity is really helpful because we can then link luminosity to this equation so that we can figure out what remember we were inquiring stuff. So we can actually calculate or estimate how far away these stars are. Distance from stars. Okay, so we can calculate. And then for stellar radii, we looked at, wow, so bright, but also so colorful. The twinkling lights as color. Okay, so when we think about color, we can actually think about the wavelength, and not any wavelength. Okay, we are looking at, once again, this is a graph of intensity, but now this is a graph of intensity against lambda. So we are looking at the peak wavelength. Okay, so the peak wavelength of different hot and cold. I mean, hot, they're all stars. What am I talking about? Okay, so at the end of the day, what we're measuring is the lambda maximum of the light from stars. Okay, so once we have lambda maximum, we can then use the equation of, remember, your lambda is inversely proportional to t. So I'm gonna write that in a different color for you. Lambda is inversely proportional to t. This is your Wien's displacement law. Wien's displacement. And from this value of t, I mean, we can use inversely proportional, or we can say lambda is equal to b, the proportionality constant over t. Okay, we got either way. Okay, doesn't matter. We can bring these two together using our good friend Stefan-Boltzmann law. Okay, so Stefan-Boltzmann basically just ties it all together. It says that the intensity is proportional to temperature to the power of 4. But intensity is actually radiant flux intensity. So for star, we can put F. Okay, and from here, we actually have the equation of luminosity is equal to 4 pi sigma r squared t to the power of 4. Noise. So we actually have quite a few equations. This one, then we have this one. Okay, but look, you guys, we can actually find temperature. Okay, plug it in here. Okay, so you can see using Wien's displacement law, we can find the temperature. Do I keep this is radius of the star? And from here, we can actually estimate. So number one, we can estimate distance from the stars. I mean, from the stars to the observer. And this R here is our stellar radii. Or, let me move this a bit, radius of our star. Size of the star. Okay, and you can also probably tell that there is also a value of L here, luminosity. Just like you can also find temperature. Okay, so you can already see that questions can be different format. Okay, they can pick and choose, but at the end of the day, when we look at the star, what we are measuring is actually the EM radiation. What we are actually observing is the EM radiation. On one side, we looked at the intensity, and then we use our understanding of standard candles to actually measure the distance of these stars from us, from the earthbound observer. And then we looked at the wavelength. And using Wien's displacement law, we know that wavelength is inversely proportional to temperature. And just based off this, we also know that because it's inversely proportional to temperature, then if we want to find the size or the stellar radii, the size of the star, we can use I mean, we can just link this temperature to here. Okay, this is your T. All right, so that's it in a nutshell. All right, so we managed to answer the 2 questions, you know, when we started the chapter. How far away are these stars and how big are they? In the next subtopic, we are going to look at, are the stars moving? So that will be the next one here. Okay, so stay tuned and I'll see you in the next video. Bye-bye.